We now consider some examples of integration by parts, just some variety. And one of the things that's often asked is how, as a student, do you select the u and the dv part? Unfortunately, there's no hard and fast rules, but there are guidelines or suggestions. Keep in mind, there's only so many choices. This is not like choosing a breakfast cereal. There's maybe 1, 2, or at most 3 possible choices or ways to split the function into u and dv. So worst case, you try one and you see what happens. One of the things that can guide that search, though, is that you know you're going to differentiate the u. So if u prime is simpler than u, that's usually a good thing. The second thing to look for is we're going to be integrating part of it. If the integral of the dv is going to be simpler, that's a good thing. That's not as common. Usually a better guideline is whether you can actually integrate the dv at all, and we'll see that appear as we go through some examples. So the main guidelines are, is u going to be simpler when we differentiate it, and are you able to integrate the dv part by itself? Let's take a look at this. So here we have an x and a cos. We can certainly differentiate x, and it'll be simpler when we do so, and we can definitely integrate cos. So let's go with the same pattern we saw in the last example and let u equal the x part and the dv be the cos of x dx. All right. We'll do this example in a way that would be more typical, with a few fewer steps actually demonstrated. We'll go straight to this term here. If we've got u equals x, then the derivative du dx is going to equal 1. In practice, we would write this out as du equals dx. So we would not usually write the dx in the bottom, we would implicitly move it up here. The other part is that we would integrate both sides of the dv side, and that would give us a v equals, what do I differentiate to get cos? We differentiate positive sine. All right, the 3 important building blocks for the integration by parts formula are this, this, and this, in that particular order. Because we're going to let this particular part, the x, be our u, everything else is going to be dv. And so our original integral, we usually just call it I, make that clear up here, can be replaced through the integration by parts formula as u times v, x times sine of x, minus the integral of sine x and simply dx on this side. And that looks nice. We'll just label the parts here for reference. And there we got v du. Okay, so again we ask ourselves, have we created a simpler integral than we started with? We absolutely have. So we've got x sine x is now outside the integral. We no longer have to work with it at all. And we have the integral of sine x. Well, that's simply negative cos of x plus a constant. Again, we don't need to put the plus constant here in the integration by parts stage, because we will have an integral at the end to evaluate, and we get it here. Last but not least, we just tidy that up. This is about as far as the simplifications usually go until we have an application. And that's it. The integral of x cos of x, the antiderivative of that, would be x sine of x plus cos of x. And again, we could verify by differentiating. It gets a little tedious after a while. We have some faith that the integration by parts method works, so we go ahead and we call that done. What if we get a slightly more complicated example? And also remind ourselves of what to identify in terms of integration by parts or substitutions. Here we might be tempted to try a substitution. We have an x squared and its derivative. But remember how integration by parts works. We're going to divide by the derivative of our substitution, and dividing by 2x is not going to make this any easier, because the x we're looking at is inside a cosine. So you can try substitution. Again, worst case, it takes you a couple of minutes, but it doesn't get any easier, and so you'd go back and try something else. Okay, same strategy as before. We have an integral with an x squared and a cos of x. Integrating x squared doesn't make it simpler, so our most typical choice here would be to let u be the x squared part, and the dv would be the remainder, the cos of x dx. Do the same thing as before. This time we get du equals 2x. Again, it'd be du dx is 2x. And on the integral side, we would have v equals, what do I differentiate to get cos? I differentiate sine. And once again, we would rewrite this. We'd erase the dx here and bring it up to the other side. Dx goes up. And we now have our building blocks. We have u, we have v, and we have du. So if we call our original integral I, we can rewrite our integral using the integration by parts formula. We won't put quite as many underscores here, or under labels, but we have u times v minus the integral of v du. So that is x squared times sine of x minus the integral of v du. So minus the integral of sine x times 2x dx. And we tidy that up a little bit, just get rid of some brackets for clarity. Also bring the 2 out front, so we get integral of x sine of x dx. Okay, now we ask ourselves, have we gone in the right direction? Have we done something sensible? I think so. Before we had x squared cos of x, now we have x to the 1 sine of x. So this is now a simpler integral. Unfortunately, it's still not quite simple enough to evaluate just by inspection. But what we could do is apply integration by parts again. Yes, of course we could. So what we're going to do, and you'll see this in the homework as well, is we're going to define or focus in our attention on this subintegral. So we know this part already. Now we need to evaluate this new integral as part of the original problem, and we'll focus in on that now. Actually, do this on the next page. So our I2, which is the integral of x sine of x, we'll leave the constant out, it'll just confuse things. We'll deal with it at the very end. Well, we can do the same thing we just did. Select our u and dv, and again, we'll pick u to be x, because if we differentiate it, it'll actually disappear, and that's exactly what we want this time around. And our dv will be sine x dx. We integrate both sides here, we differentiate here, we'll get du is equal to 1 dx, and here we get v is, what do we differentiate to get sine? We differentiate negative cos. Those are the 3 ingredients we need, and we need them in this triangular form. So our integral up here can be replaced by x times negative cos of x minus the integral of v negative cos of x, be very careful with your bookkeeping on these problems, dx. And that we would rewrite just a tidying phase, x cos of x with a negative out front, double negative here, so it's plus the integral of cos x dx. And this we can actually evaluate. What do we differentiate to get cos? We differentiate sine. So at the end of the day, this will be negative x cos of x plus sine x plus a constant. All of this is just the I2 integral. So if we go back to our original function and its integral, remember what we had. We had x squared sine of x, and flipping back one page to check, we had x squared sine of x minus 2 I2s, minus 2 times that second integral, and now we have that second integral is here, x squared sine of x minus 2 times minus x cos x plus sine x plus a constant. As we just tidy that up for organization and aesthetics, we'll have a plus 2 x cos x, a minus 2 sine x, and a minus 2c. We can leave it like that. Some people, if you've seen integrals before, you might have replaced this with a new constant. Please don't replace it with c. If you've already used c, you should replace it with maybe some new constant, c2 or ca or c new. But if you've already used the variable c, you should not recycle it. Okay, so integration by parts. In summary for this example, we have x squared cos x, we get x squared sine x and x cos x and a sine x, and we see there's patterns that start arising here. You can look for those. At the level we're needing it for in this class, it's best to actually go through the steps each time, I think, just to reinforce that message and allow you to handle any case that comes up. It's pretty straightforward, if a little tedious as we go through these longer examples. Again, we could always check. We could differentiate this. It would have product rules, but what we'd get is an amazing cancellations so that we only ended up with the x squared cos x at the end of the day.